I have Jim White with us. Jim is from Colorado Satellite Services in the Colorado area, which makes it easier with Colorado Satellite Services. Jim will give you some of his background, but the basic concept is the fact that he's been in the satellite business for many, many years. If you sit in this room for more than 24 hours, one of the satellites he built will come overhead. Okay? He knows what he's talking about. He's been there. He knows what does work and what doesn't work. He has had the successes and the failures, and some of the successes and some of the failures. Some of the failures are almost as fun to listen to as the successes. Okay? Because what you really want to do in this business is to kind of learn from other people's mistakes. Okay? We're headed into a phase in the next year where we're going to be working on something called a university nanosat kind of effort, developing a larger satellite than what we've done in the past. And we're hoping to gain from his experiences and his knowledge. Okay? Jim?
Thanks, Greg.
And for the next, when they show up at 3 o'clock, it'll be the same kind of thing.
All right, well, good afternoon, everybody. Always fun to be here, always fun to talk to folks who are interested in doing this kind of thing. Just very briefly, my experience goes back to the early Navy days in the early 1960s, some of the very early black satellite projects for the U.S. government. And I spent about 5 years working in the Apollo program, Apollo 8 through 17. Came back to Colorado and worked on a variety of projects. Ended up working on some of the AMSAT satellites starting in 1989, and I wrote the software for several of those, built a couple, had a hand in building several of them. The AO-51 satellite, for example, that you might know as AMSAT Echo, we did the final assembly of that in my lab, and I wrote probably 85% of the software for that. Some of which is still in use, and we're repurposing it and turning it into the command software for Trailblazer 1. So lots of fun with that kind of stuff. For about the past 6 years or so, I've been a reviewer for the University Nanosat program. I spent 10 years at the Air Force Academy as kind of the chief satellite engineer, retired from that about 3 years ago, and I'm there now just occasionally. In that role, we did FalconSat 1, which failed on orbit due to a power problem after a couple of weeks. FalconSat 2, which came crashing back down to Earth after a launch vehicle failure, and we actually got back pieces of it. FalconSat 3, which is being flown now at the Air Force Academy, and we just were listening to a pass and downloading telemetry from it earlier this morning here. And FalconSat, I retired after FalconSat 3 was launched, but then they asked me to build some subsystem modules and circuit boards for FalconSat 5, and that's being flown from the Air Force Academy right now. So I've got some bits and pieces. I think overall I've had my hands in about 35 satellites. There's about a dozen up there right now that have my initials scratched in them somewhere or another. And right now I'm just consulting to lots of folks who are enjoying building CubeSats and microsats. That was a good introduction, Craig, because this particular talk, about 55 minutes or so, is not about how to build a satellite. It's about some of the things that have come up in the way of mess-ups and errors and problems in about the past 6 months with 4 different CubeSat and microsat programs that I was asked to come and help for. And in some of these cases, I was asked to come and help like 3 days before they had to deliver, and they couldn't get the comm system to work. So part of the motivation for this talk is to try to get the word out on some of these common things that I see people doing wrong over and over and over again, so you don't do that.
Hey, Jim, if I could also, he likes interaction, okay? If you've got questions, don't just sit there with a dumb look on your face, okay? Ask him, okay?
Yep, cool. By all means. And then the second part of this talk, which we'll run through fairly quickly, I think, is once your satellite launches and you're part of one of these multiple satellite launches, which is very common nowadays, whether it's CubeSats or microsats, there is this problem with how do I first establish contact with my satellite, how do I sort it out from the crowd, how do I figure out and make Eulerian elements, which one is mine, and what do I do in those first couple of weeks of orbital operations. I tried that a minute ago and it didn't work. Okay, I guess it is going to work. There's a lag. Okay, so the first part of this, as I said, is lessons primarily in assembly, integration, and test. That's what AIT is, assembly, integration, and test. And these are, to some extent, sort of in random order, but I tried to group them a bit. So sort of from the organizational point of view, one very key point that I saw one group stumble on pretty badly, and it was a university group building a CubeSat, was they had about 8, maybe 10 key people involved. Each were the subsystem leads for the various parts of the satellite. And in this last 5 or 6 days before they had to ship it off for environmental testing, they were all involved in other schoolwork, other activities. One of them had actually left the university and was working, had to get time off work to come back. And the problem was that they had not well documented nor shared their knowledge, and they were absolutely key people. So in that 4 days, 4.5 days that we were frantically trying to get the satellite put together, we ended up spending a half a day at times sitting around waiting for a key person to come in, and very close to missing the deadline for shipping the thing. So the lesson learned there is always have at least a couple of people who have adequate and expert level knowledge on each of the subsystems, so you're not stuck waiting around for one person. The other thing that happened to us on a different project in the middle of that last few day process was there was a huge snowstorm, and people literally could not get into the lab to work on it for a day in one case. And the problem, of course, is that folks didn't get started early enough. They didn't plan for those kinds of disruptions. People can't get there on an airplane or a snowstorm. Or in another case, and I think it's on it's on this page, at the University of Colorado, trying to get the CSSWE CubeSat put together at the last minute. One of the days we were working on it was Friday. Friday afternoon was a huge football game, and guess what they do around that campus on a football game day? They close half the roads and block off most of the parking lots. And the people ended up having to walk a mile to get into the lab to get things done. So the point is, those are sort of unavoidable. Give yourself a few extra days. Don't allow this AIT process to run right down to the last minute, because these kinds of things will happen to you. Organizational logistics kind of a thing, we found it extremely useful in one of the labs to have a speakerphone that got brought in the last few minutes, because we were on the phone to vendors in that last couple of days saying, yeah, your thing isn't working like you said it would. Tell me how to make it work that way. Or in one case, we spent off and on for a 3-day period on the phone with a vendor, and the vendor kept sending us firmware updates to their device. The telephone charges would have been extraordinary for that, so we had Skype up on one of the laptops with him on Skype at the other end for 3, 4, 5, 6 hours at a time. So having a machine available that you can Skype on is very useful. And in one case, we hooked the camera up and we showed him a picture of what we were seeing. And he said, oh, yeah, well, I've seen that before. And he fixed that, sent us another update. Unfortunately, because we're doing all this at the last minute, that particular vendor was not thoroughly testing and regression testing the changes he was making to the firmware. So he sent us a couple of things where he had added a feature or fixed something and he broke something else. Again, the fundamental problem is doing things at the last minute. But the other lesson to be learned there is make sure vendors regression test their code or their firmware before they send you an update. Problem we ran into at a different place was they started assembling, this was a 3U CubeSat with deployable solar panels, and they discovered, holy cow, I don't have enough 256 stainless steel bolts, 1 1/8 inch long. They had bought a bunch 2 years ago, and they got used up and lost, and now you needed those to secure the solar panel clips to deployable panels, and they ran out. You know, where are you going to go at 6 o'clock on a Saturday night to get that particular piece of hardware? Fortunately, they had a hardware store next to them that's one of the biggest hardware stores in the country, and they were able to go get them. But where would you find them here in Albuquerque? My suspicion is you're not going to find those locally. So always give yourself a number of extra pieces of wire, fasteners, connectors. Always buy a few extras so that those are available to you at the last minute during AIT. It's also a good idea as you get about 6 weeks away from your final assembly and integration and test to do an inventory of all that stuff, to make sure you've got not only what you need on hand, but a few spares as well. From a test plan point of view, when you get to assembly, integration, and test, you are doing some testing of the final assembled product there, your flight unit. Write a test plan well ahead of time that specifies exactly what you're going to do to verify the functionality and the proper operation of each piece of that fully integrated satellite, and then stick to the plan. If you end up having to deviate from the plan, make darn sure that everybody representing the expertise of all the various subsystems is in agreement with that deviation from the plan. A couple of years ago, I was involved in a project where one of the senior leaders came in and was observing things and convinced them to deviate from the plan, and they ended up frying the batteries. So write the plan very early, make sure everybody's in agreement with it, sign off on it, don't deviate from that plan. It's easy to get distracted and diverted and say, oh, we forgot to test this, so let's throw that test in and cause yourself some problems. The other thing that I've seen happen over and over again to people, particularly when they go into environmental testing, is they write the environmental test plan. They go to wherever the environmental test location is. You work your way through all the environmental testing. You make a few notes on the results. You pack your satellite up. You go home, and the test report never gets written because everybody's too busy getting ready to ship this thing off to launch it to sit down and write the test report. Well, guess what? The environmental test report is a deliverable to either the integration contractor or the launch vehicle contractor. The way to do that best is, as you arrive at the test facility, make a copy of your test plan, rename it test report, and then sit there and fill in all the results as you're going through the plan. That's the only way I have ever been successful or seen people be successful in cranking out a complete and accurate test report. As you do that, it's a real good idea not only to fill the results in the various places in the test report, but to keep a running log, just a narrative as a Word document, for example, of everything you do, step by step. Joe arrived having overslept. You know, see that line in a narrative from a test plan, but more likely it's reached 10 to the minus 5 tour at minus 30 C, turned on the satellite, nothing happened. And then what are the diagnostic steps we followed to figure out we forgot to plug the cable in, and now we turned it on and it worked. It's very important to do that kind of thing. Where that really comes in handy is now you get on orbit and you fire up your satellite, or you're 2 or 3 years into the mission and you turn on one of the experiments, something anomalous happens, go back and look through that narrative and see if you ever experienced that before. Don't rely on people's memories. I'm going to learn to be a weatherman here and push the button about 5 seconds before I really am going to switch to that page. One of the projects that we just finished up at another school had a significant issue because they were scrambling to change firmware to make things work the way they wanted it to right down to the last minute. But the mechanical structure was designed such that once they put the solar panels on, they couldn't get them off again. The solar panels had to be off in order to plug in an umbilical to update the firmware. If they had had to take it apart, they would have broken a solar panel. That's the only way they could get it apart. Can't do that, obviously. This is the one and only flight article, right? So Who's the mech person in here? Somebody said they were mech, yeah.
Yeah.
Make sure the mechanical design is such that you can take it apart at any time and put it back together again. And another kind of a key clue there is you end up staking bolt heads. For what, you know what, this is a test. What's the torque spec on a 440 stainless bolt? Yeah, it's 4 inch-pounds. Do you know how much an inch-pound is? That's like you take a wrench this long and you kind of go, and that's 4 inch-pounds. There's no way a 440 stainless fastener will remain tight in a vibration test. 10 G RMS for 3 minutes into the bottom of a satellite this big, I guarantee you 440s will back out. So you always have to stake 440s. If you stake them with epoxy, you're probably going to break something getting the epoxy off and try to get that bolt out. So stake them with RTV, the kind of RTV that does not harden fully. It's like bathroom tub caulk, right? Loctite is fine. Make sure you use the right kind, though. You want to use the stuff on your threads that hardens in the absence of air, not the, and I always forget which is green and which is red, not the one that hardens when it is exposed to air. Use the wrong kind, you end up with goo in the threads, and then the goo gets all over everything. So stake them with RTV because you can always pull RTV off. It's messy. You got to be careful. A vacuum cleaner hose helps with that. Don't succumb to the temptation to stake things with epoxy. Okay, we talked about providing the ability to load firmware at any point during your final assembly, even after you're fully assembled. Battery voltages. This is a double E design kind of idea. Who's the double E folk? Somebody said double E? Great. Project we're helping with just recently, their design was such that as the battery voltage sagged, but before it got to the point where it went around the knee of the curve, so it was still within the operational range of voltages, they were only half a volt from the overhead of a low dropout regulator. Well, even an LDO will start sagging, and an LDO will just follow that input voltage right down, all the way to zero if it goes that far. So what was happening, it was a design flaw. They didn't allow themselves another volt of battery voltage over the dropout point of the LDO, even when the battery was fully discharged. So guess what was happening? The processor was resetting because the regulated voltage was dropping below the brownout voltage of the processor. Second part of that was they had the brownout voltage of the processor set too high. It was a processor that could run all the way from 3.3 to 5. They had the brownout set, I think, at 4.2. And the regulated voltage was dropping to 4.1. The processor was going below the brownout voltage. I'm gone. The threshold below that was 3.8. The processor would run fine there. Wouldn't run as fast, but it would run great. That's what we ended up doing to solve the problem. So, a big do not here. This was on a similar project. It was actually one school doing 2 different CubeSats more or less at the same time. They were using an AstroDev helium radio, just like we're using on Trailblazer 1 here. You power the intelligence and the microcontroller that's in that radio from 3.3. You power the power amplifier from some other voltage, preferably somewhere between 5 and about 10 volts. They had decided to power the power amplifier from the regulated 5 that was the same voltage they were using to run the commanded data handling processor. Every time they transmitted with the power level at about 3 watts, that 5 volt regulated would sag below the dropout voltage of the commanded data handler processor. But it was right on the margin. So it didn't do it every time. It just did it occasionally. So it's one of these problems that doesn't happen every time, intermittent kinds of things. How the heck do you figure that out? Well, we finally put an O-scope on the 5 volt, and sure enough, it's bouncing like crazy every time the transmitter transmits. So we ended up hacking the EPS board, cutting a couple of traces, and putting in a number 24 jumper to route raw battery voltage to that power amplifier rather than a regulated voltage. So there are 2 problems with doing that. One is it's going to bounce the regulated voltage around, And that regulated voltage isn't supposed to move. There are some things connected to it that are counting on it not moving, including potentially the reference voltage to A to D converters. And the second problem is you've killed yourself in terms of efficiency. The 5-volt regulator is anywhere from, what, 40 to maybe 80% efficient, depending on what kind it is. So you're losing somewhere between 60 and 15% of your power by running a power amplifier through a regulator. One of these projects that I've been describing, we were having a terrible time at the last few minutes there because they had not put test points on their PCBs that let you get in there and probe things and see what was happening. For example, there was not, in the last example, an easy way to get an O-scope on the output of the 5-volt regulator. It's a very dense board, lots of surface mount parts. So now I've got 2 magnifiers on in addition to the close-up view in my trifocals, and I'm trying to see where to put this scope probe on a one and only flight article to figure out what this problem is while somebody else is running the software. That's not a good way to do things.
Do you ever put heartbeat LEDs in?
Sure. Yeah, that's very common. I tend to do that on my C&DH processors, and that's fine. But if you do that, remember they're going to draw some current. So put in very large current limiting resistors, so that, on the order of 10K or so. So the LED will illuminate. It's not very bright, but you can see it in the lab. That's all you need. GPIO pins also. GPIO pins you tend to use to turn things on and off or to sense whether something's on and off. Put in test points for those if you possibly can. Another project we were working on, somebody had told them, or they might have looked it up on the web somewhere, that you need to set your deviation for 9600 bit per second GMSK to 7.5 kilohertz. 7.5 kilohertz will deviate out of the receive bandwidth of most of the receivers that we use to hear these satellites. I think it was probably a misunderstanding. What the person on the web was recommending was 7.5 kilohertz total occupied bandwidth instead of deviation. So deviation times 2 is total occupied bandwidth. The right deviation to set for 9600 GMSK is 3.5. And you'll get the kind of pattern that I drew up there on the whiteboard if you look at it on a spectrum analyzer. Another point that some people sometimes trip up on with particularly these multiple launch payloads, where you are required by the rules of engagement to delay 30 to 45 minutes to as long as an hour before you turn on any transmitter, or in some cases before you turn on anything. You've got this separation sequence that then you go through. You start a timer, and after several minutes, you maybe deploy solar panels, you wait a couple minutes, you deploy antennas, maybe deploy a boom with a magnetometer on it, those kinds of things. When you are writing your firmware, put in commands that allow you to do things like override that separation sequence so it doesn't happen. Otherwise, you're sitting around every time you power up waiting for 45 minutes for your command and data handling processor to come on. Put in hang on one second, put in another command that just shortens that time. So it starts maybe 30 seconds after your power up. Put another one in that defeats it entirely, and then put another one in that triggers it to happen without having to do the power up. All of these things are necessary to be able to test that without sitting around for hours, or indeed creating a danger for somebody working on the physical article, and you power up and forget, whoops, that boom is going to pop out in a few minutes. Yeah, great.
Why don't you just turn on the power and the radio once you come out of V5?
You can turn on the power to the radio, you can power up, but the rules of engagement generally are thou shalt not transmit for n number of minutes. Okay. For example, there's nothing that says that you can't power up and start taking data as soon as you separate off a light band for a microsat or pop out of a peapod. The rules are you can't transmit. And the reason you can't transmit is everybody else is real close to you. You don't want to transmit directly into somebody else's receiver and cause them problems. By the way, if you are thinking about putting a camera on your satellite and taking pictures immediately after separation of the rocket and all the other satellites coming off, be sure you understand that you've got to get the launch vehicle's permission and all the other satellites' permission before you take their picture. And some launch vehicles are extremely sensitive about that, and some of them will just flat tell you no. Diagnostic outputs to the umbilical. Okay. Anything I've ever built, I've got a serial umbilical over which I can control the satellite, send commands. It's like having the ground station plugged directly into it. But it's more than that, because it's a great place to spit out like printf statements into a serial port to tell you what's going on in the satellite. Now, of course, you want to turn those off before you actually launch it, because you don't want time being used up spitting data out to a UART that could be used for other things. But be sure you build that in, use it for that purpose, be able to turn it off or send a command to the satellite that turns it off as you're doing your AIT. One of the very helpful things to put into that is the status of all the I/O pins, the status of a USB port or 422 port or that kind of thing. So for AIT itself, when you're building that plan, the question is, what is testing? What is it that we're really doing here? Well, what you're really doing is half of what in the industry we call V&V, verification and validation. So what's the difference between verification and validation? I go to the NASA standard, and the definition is actually matched in the ESA standard when I talk about this. Verification is finding out if it works like it was designed. In other words, does the design meet the requirements that I was given? Validation is, does it do what the customer wanted it to do? And those are different things, and you have to kind of think about that a little bit. So did we build what the customer wanted? How many layers of translation are there typically in a satellite project between the customer saying, I want something that'll take pictures, polychrome, 10 millimeter resolution from an 800 kilometer orbit, through the engineers and the politicos and the bean counters, and it finally gets down to the people who design the camera, and it won't do that. There may be good reasons it won't do that, but there's also lots of opportunities for things getting lost in translation. So the way I remember that is, verification is, did we build it right? Validation is, did we build the right thing? The thing to remember about both of those is they are based on requirements. They've got to be driven by the requirements of the project as a whole. So when you get to verification, the question is, what are the methods of verification? Lots of ways to do verification. Examination, inspection, similarity. Only a piece of verification is testing. So what's examination means? It means I can pick this up and I can look at it. Perhaps I'm looking at a label or something, and I can see that it is labeled widget XYZ serial number 27, and that's what I'm supposed to have. The difference between that and inspection is inspection tends to be measuring something. Now I'm going to see, is it in fact 3.27 inches long, or X in diameter, or does it have a DB9? Okay, that's inspection. Similarity is, does this look just like this other one? I got two of them, they look identical. Okay, it's similar to the one that I've used before. And then for testing, there are a zillion different ways to test, of course. A simple kind of a test is a fit check. In any kind of satellite program, you end up having to do that. If it's a CubeSat, you end up having to take it to Cal Poly, see if indeed it goes into a P-pod, does not rattle excessively, and when you tighten the screws, you've got the lateral distance correct as well, so things tighten up. If it's a microsat, you end up doing a fit check to a light band, or your light band to the launch vehicle ring interface. There are also fit checks internally as you bring subsystems in the satellite together. Do they in fact go where they're supposed to do? Do the bolt holes line up? I'll give you a good story about that. When we did the FalconSat 3 integration at Cape Canaveral onto the first ESPA ring. Are you all familiar with an ESPA ring? What they look like? The ESPA ring is for launching multiple up to 200 kilo satellites. they sit on top of a Atlas V or a Delta IV. And it's a big ring with a bunch of holes in it. And around each hole, there's a flat plate with, I don't know how many, it's about 50 bolt holes. And on top of that, the whole thing is about 9-10 feet in diameter. So you hang a whole bunch of satellites on the outside of it. And then on top of that, there's another big ring that's about a 6-foot diameter with a bunch of bolt holes. You put the big satellite on top of that. In this case, the big satellite was called Orbital Express. So the 5 of us that had the small 150-kilo satellites came to the Cape in a big clean room, one at a time. We went in, did our final testing, did our final cleaning, moved the satellite over to the ESPA ring. The technicians there then took over, bolted it onto the ESPA ring. They bolted them all on. We all left. We were the last ones. In fact, we were at the Cape, and we had like 2 hours to get your plane out of Orlando. So we beat feet for Orlando down. The next day, they brought in Orbital Express, set it down on top of the ESPA ring, started dropping in the bolt holes, and they didn't fit. This ring had been distorted about 20 thousandths of an inch by the weight of the small satellites hanging off the edges of it. So what they had like 4 days to finish this up before it had to move to the Cape for the launch. What they ended up doing, blew me away, was put a turnbuckle, cable turnbuckle, across the top of the ESPA ring, tightened it up while they very carefully gauged that until they had pulled it in 20 thousandths of an inch, dropped in the bolts, tightened them up, and away they went. What they told me was that if it had been 40 thousandths of an inch, they wouldn't have done that because there would have been too much lateral stress on the bolts once they were all tightened down to meet the tolerance and the spec on the bolts. So I don't know whether that's true or not, but that's what we were told. We were happy because we made it into orbit. What other kinds of tests do you do? Hardware in the loop, obviously. We're starting to do that right now with Trailblazer 1, where we've got the actual radios in the circuit and the ground station in the circuit. Stress testing. I can't overemphasize for the firmware folk the need to test how things work outside the normal bounds of what you would expect to have as inputs. When we teach this kind of thing in another course, we have a little ISAT, a classroom satellite, a test satellite that you can sit on the bench. And one of the things we have the students do is set the clock. And a lot of the student groups will sit there and they'll set the clock for 1 hour, 1 minute, 1 second. They'll watch it count up. They'll set it for 6 hours, 20 minutes, 35 seconds, watch it count up, call it good. What they're supposed to find is that we have an intentional firmware in there, an intentional firmware error. If you set it for 60 minutes, it'll take it and it'll count up to 61, 62 and drop to a negative number. You should never be able to set a clock to 60, right? 59 is the highest number, then it goes to 0. So that's an example of write your firmware and have somebody else test it and have them test the boundary conditions. So those are the kind of things that can kill you. Plugs out testing means you've removed all the remove before flight covers. You've got it in the full flight configuration. Day in the life is you run an entire 1-day cycle, including the eclipses and the temperature changes and the illumination changes, watching the battery sag as you go into eclipse, come back out again, and so forth. From a software point of view, white box testing is testing a chunk of software when the testers know exactly what's in there and everything it's going to do and everything to expect. Black box testing means the testers don't know the way it behaves. They're given a list of things that it should do, and they try to break it. Ticking box testing means it's got errors in it, and no matter how hard you test it, eventually it's going to blow up. And that applies to the vast majority of firmware. Another note here is that validation, remember what validation is, that's checking to see if the customer is getting what they want, often takes place at the same time as verification. You can quite often do them in parallel, but in fact they are two different things. Can you advance me one, Brian? The button didn't work. Try it now. Okay. All right, so some other lessons learned here. Do not assume when you get down to that last week of AIT that all the pieces are going to fit together that you've never tried together because they won't fit. Long before you get to AIT, test the ground station and the satellite. One of the things that I recommend is take the satellite, stick it in a truck, take it 10 to 15 miles away, top of a mountain somewhere, test it with your ground station over a distance. That's a great confidence builder. You find out things are really going to work over some distance. It gets you away from the multipath problems that you have testing over RF inside labs. And you get some sense of what the relative signal strengths are going to be. It's a good way to verify, for example, that the transmit antenna in the satellite is actually working. It's very hard to tell that when you're sitting in the lab. Make sure you have good voltage versus current curves for your solar panels. Around here, on a good clear day, you can probably get about 75 to 80% of the current off a solar panel that you're going to get in space if you just take it outside. You're better off if you can get up at altitude. In Colorado, we tend to take our solar panels up to the top of the 14,000-foot mountains. At 14,264, we get 92% of the power off a solar panel that we'll get on orbit. So it's a great test and a great way to do an IV curve. Already, last bullet there is a duplication with an earlier one. Okay, these last couple are all from one particular satellite that we were throwing together at the last minute. They were using a JTAG interface to program it and to watch diagnostics while they're putting these last firmware changes in, and things stopped working right. Well, a JTAG interface actually runs code in the microcontroller that you're trying to test, and that'll use up cycles. It'll screw up streaming data when it's coming in at high bit rates like 115K2, and it can't keep up with that streaming data, and it'll also screw up the timing loops. So things don't happen in deterministic intervals like they're supposed to. So don't do final tests with a JTAG interface. Always make sure you power off things before you plug or unplug anything. I went to lunch, I came back, they had spent an hour trying to figure out why the processor kept resetting on them. It was resetting because they were plugging and unplugging a powered USB interface while they were running. And they were doing the same thing with the JTAG interface. It's always a good idea to run your EPS from a solar simulator power supply, and do that early on to make sure that EPS is working right. Don't supply it with a power supply emulating the batteries. Supply it with a power supply emulating the solar panels so you can make sure that your EPS is doing what it's supposed to. I always keep a digital voltmeter, a bench digital voltmeter sitting on the bench, connected to the battery supply, and watch that right there, right in front of my eyes all the time while I'm testing, so I don't accidentally pull the battery voltage down below where it should be, and also to give me an idea of how things are operating. Always keep a logic analyzer on hand, one that can read out things like SPI and I2C buses in English so you can really see what's going on. They're a fantastic tool for debugging things, and this goes back to having those test points on your board so you can easily clip them in there without risk. Ground station radios. There are some radios out there now that are designed for other purposes, like amateur HF, that they have tacked on UHF and VHF bands, and they don't have the same features that you find in radios that were designed for satellite use. Ran into that on one of the projects. We never did get that radio to work right on the downlink from the satellite. Had to go grab one from a guy's home, a satellite radio, and bring it in. And now they're scrambling around trying to find a used version of that same radio. A spectrum analyzer, like displaying your downlink all the time, will tell you right away if something wacky has happened with the downlink. So I tend to keep a spectrum analyzer running all the time. And I also keep a oscilloscope. I have a picture of it. Yeah, I keep an oscilloscope on my downlink all the time, showing me the eye pattern of that received data. It's a great way, you see right away, not only when you're testing in the lab, but when you're on orbit, what the quality of that downlink signal is. The The ideal pattern is the one in the bottom left-hand corner. Well, the ideal actually is the top left-hand corner, but you'll never see that. The bottom left-hand corner is what you might typically see where the radio is off-tuned just a little bit. The top right-hand corner is pretty typical for a downlink. The modulation is a little asymmetrical, but that's not unusual for the kind of radios we use. The bottom right-hand corner is a good example of interference on the downlink. It's hard to get an RF link to work in a lab. Too much multipath, too many reflections. The secret to getting it done right is use dummy loads, get your signal levels down so you're not overloading, and if possible, use some RF absorbers around the room so the RF isn't bouncing off the walls. Computer noise is another thing that'll get you. When you're testing devices, get them away from the computers as far as you can, particularly the monitor cables. Never let your radio, particularly the satellite radio, transmit into an open or to a short. Always be sure there's a dummy load on every transmitter. Your flight satellite antennas mounted to the satellite. So you got your 100 kilo ESPA class satellite sitting in your clean room, you got the flight antenna hooked up to it, and you're radiating into the flight antenna. Not a good idea. That flight antenna will not be 50 ohms, and you'll get reflections from the antenna back into the transmitter. No antenna is 50 ohms when it's sitting in a room like this and there's things next to it. Those things disturb that pattern and change the impedance. So I'll let you read for yourself there the next bullet item, which is the way that I tend to hook things up with radios when I'm testing in the lab to minimize the multipath and to assure I don't overload a receiver. You can hook transmitters and receivers directly together. Just make darn sure that you've got adequate attenuation in between them. If you hit the typical gas-fed front-end receiver with a watt right out of a transmitter, you're going to cook it. Calibration. There's several charts here on calibration, and I'm going to provide this set of slides to Brian and the guys here, and they can distribute them to you. So I'm not going to go through calibration in detail. But a very good point here is that your analog sensors all have to be calibrated, and it always takes a whole lot longer than you think it should, particularly when you have to run an analog sensor over 5 or 6 different voltage swing points over a dozen different temperature ranges. It can take days and weeks to calibrate 100 or so analog data points. And again, I'm going to skip over the details. There's an example in here of an issue we ran into with the AO16 satellite. AO16 had 183 analog telemetry data points. What we discovered 2 years after launch, as I was doing some telemetry analysis, getting ready to do a paper, was that 5 of those data points were mislabeled. So we got 5 analog telemetry points that we've been reading wrong for 2 years. Now, it turned out they were all temperatures, and the temperatures were not a critical part of the operation of the satellite, so it wasn't really affecting anything. And what happened was you got 5 values. You can see the before and after here was somehow when we were recording these, doing about 3 weeks of calibration, we got them rolled. So this one was actually that one was that one, that one was that one, that was that one, right? Simple clerical error. As a final test, as I said, take it out a couple 3 to up to 15 miles away and test the flight article and your ground station. Okay, now I want to spend about 10-15 minutes talking about early operations. We'll run through this kind of quickly. This is what happens after launch. How do you figure out which satellite is yours? How do you do that initial establishing contact with it? So the first thing to keep in mind is that on your ground station, you got to be ready. And one of the things that is part of being ready is to make sure that your clock is correct on all the computers in the ground station. It needs to be at least within 1 second. If you can do better than that via an internet NTP protocol, that's great. If the timestamps on your sensor data from a science instrument, for example, for when you receive it on the ground are more critical, then your time needs to be closer than that. Check the antenna calibration. Check it ahead of time and check it at least once a week. At one of the ground stations I deal with regularly, the antenna rotators just through daily operations of 6 or 7 passes, will get out of calibration by as much as 10 degrees in a week. One of the antennas is a 12-foot dish. And guess what? A 12-foot dish at S-band, you're not in the beam width of the antenna anymore when it's 10 degrees off, not even close. Your calibration of your antennas is true north, not magnetic north, true north. Compasses are useless when it comes to calibrating antennas. There's all kinds of software out there you can use to point antennas. You guys are using Nova and I think a couple of other solutions, and that's great. There's others as well, some free, some pretty expensive. OS Comet is about 50 grand, I think, when you buy it off the top. Further prep, watch out for operating system upgrades on computers. And one of the military ground stations we deal with, there's so much anti-spyware, anti-do-anything-bad, anti-virus crap on them that we can't even run the ground station software. We ended up taking them off the network, have them wiped and re-imaged, load the minimal of what we really needed on it, and never plug it back into the network. Just if you plug it into the network, the military security forces are going to download so much crap into it, you won't be able to run the ground station software. But even if you're in an environment like this, an educational environment, and you don't have that kind of issue with the paranoid idiots that run military networks, watch out for the automatic upgrades to the operating system. A couple of things, different things I've seen happen. One is you're sitting there in the middle of a pass, and Windows decides it's going to implement an upgrade and download it last time. You lost the pass, right? The other thing I've seen happen is you get a download of an update, you say, well, okay, it's from Microsoft, that looks great, we'll let it go. And guess what? It breaks your custom software that you wrote because they changed the way they do something internally within Windows. So my rule of thumb is avoid Windows. But other than that, once you have approached AIT, you establish the software versions of all the computers involved in this project. You get them off the network, never change it for the duration of the project. Now, that may seem like overkill, but I've seen so many people stumble on this, and I've been bit by it myself so many times. XP to Vista is a classic example of that.
So Jim, I have a question.
Yep.
Would you suggest having, kind of like a clone image of for us, the XP and just leave it
You bet.
the way it is after?
Yep. Yeah, that's another good idea is once you've established the baseline of the software on all these computers, image them twice. I carry one around for my ground station computers in my lab. I carry one around in the trunk of my car. So I don't want the house to burn down. I got one in the fire safe. One's in the computer, one's in the fire safe in the lab, and the other one's in the trunk of my car. That's the ultimate in paranoia, I suppose. Okay, there's a whole section here on how deployments happen from, particularly with CubeSats. I just skipped over a bunch of slides there because that's kind of beyond the scope of this discussion. But it's important to note that what does happen when either microsats or CubeSats come off a launch vehicle, in that first orbit or two, they are right next to each other. And when you plot them on a piece of tracking software, the names, there's 4 satellites there, they're all plotted right on top of each other because they're within a few kilometers of each other. At this point in time, well, before the launch, you've been given a set of pre-launch KEPs. So you can do your planning for that. But about the only thing those pre-launch KEPs are good for is figuring out when to come into the ground station to expect it to come over. Within a few hours of the launch, you'll get their best guess at what the actual Keplerian elements are as a result of what orbit the rocket actually hit and what really happened during separation. But those are also just sort of tune-ups from the pre-launch KEPs, and they can often be inaccurate until the satellites have gone over enough of the sensors and the JSPOC network for them to actually get hits on enough of them to derive a good set of elements. Sometimes that can take a couple days, in spite of the fact that they are tasking multiple sensors to do just that, because they want to know where all these things are. So the pre-launch KEPs are kind of good for planning, but within a couple of 3 days, you ought to get good KEPs. The problem is, with a whole bunch of CubeSats on the same launch, they can't tell them apart with those sensors. You sometimes hear that NORAD's tracking 75,000 objects, whatever the heck it is. Well, that's true. But if you pop a dozen 1U CubeSats with VHF and UHF antennas on them out of the same launch, they can see them. The limit is about 10 centimeters out to 800 kilometers. They can see them. They can't see them with very many sensors, and they can't tell them apart. So how do you know which one is yours? Well, you don't. What you get, what they publish, is a set of Keplerian elements, since they don't know which is which, that says the object numbers will all be the same, followed by A, B, C, D, E, F, however many there are. I saw one of these that was 17 objects. And it turns out that about 6 of those objects, they could figure out what they were, because one was the rocket body. 2 of them were bigger satellites. A couple of them were 3Us. The rest of them were smaller CubeSats. Couldn't tell them apart. So what do? You're the owner. Where do you point your antennas? Well, as it turns out, you can point at the center of the group for the first few days, maybe up to a week, and you're fine. Because the beam width of your VHF, UHF antennas is typically about 15 degrees. And they're within a couple of degrees from the first object to the last. So for the first week or so, you can just point at the center of the group and you can start your operations. But as they begin to spread out, you need to start being in contact with all those other owners. Because what happens here is it's up to the owners of the satellites to figure out which one of those element sets belong to them and tell the JSPOC, I'm Object C. Please change my name to Trailblazer 1. Right? The problem is, you better be in contact with all those other people because somebody else might think that one is theirs. And if 2 people tell the JSPOC, I'm Object 2674C, guess what the JSPOC is? A, your credibility goes to the toilet. B, they send you both back a message and say, you guys get together and let me know in about 6 months when you figure it out. So in the meantime, your name doesn't pop up on the elements, right? They have very little patience with that. So what do? Get yourself an email or a chat group going with all the other owners, and everybody share the information. So then, as they start crossing the horizon, as they start spreading out a little bit, they start crossing the horizon both at AOS and LOS a few seconds apart. Now, if you set your satellite up so that it beacons fairly quickly, on the order of a minute or so, you simply point your antenna at the place where they're all going to come over the horizon, because for the most part they're in the same orbital plane. And you listen for yours, and you've got this kind of display up on your tracking software. And when you start hearing yours, you look to see which of those coverage circles, the footprint of the satellite, just crossed your ground station. And then you do the same thing at LOS when it goes over the hill the opposite direction, right? You do that a few times over a few days, and you'll be able to pick out which one of those element sets is yours. Then coordinate with everybody else. Get on that chat window and say, hey, I think I'm Object C. Anybody else think they're Object C? Good, fine. Now I can tell JSPOC that's me. Okay, so summarizing that, plug all the element sets into your tracking program as A, B, C, D, E, whatever. Delete the ones that you know are not confused, or the ones that have already been labeled, unless you're interested in continuing to track the rocket body. Make sure your automatic beacon is on. After your first few orbits, when you've got your first few blocks of telemetry from the satellite, you're sure the power system's working okay, consider turning that beacon rate up to make it a little more precise in timing those horizon crossings. And then be sure your horizon is right in your tracking software. Earlier today, we were listening to FalconSat 3 on the pass, and as it went over the hill that way, we lost it about a minute before our tracking program said we should have. So it went behind the building. You've got to build the building into your footprint of your tracking program so you know when you really are going to lose the satellite. Okay, so we kind of went through this. This is a summary of everything I just said. The box at the bottom there is a reminder that it can take weeks to to sort out who's who for sure. So be patient with that. The thing you want to be careful of is as they start separating to the point where you can't any longer be assured of reliable communication by pointing at the center of the group with your antenna. Don't start some process on a satellite that requires you have communications with it for the next several days. Because you may spread out just enough over that period of time, pointing the center of the group won't work anymore. Now you're in the mode of fishing around for which one is yours by timing horizon crossings and moving the antenna during the pass while some critical operations going on. So my general rule of thumb is do your processes for making sure your bus is working right. Maybe do the early checkout, just turn it on, run it for a few minutes of the experiments, and let things settle down so you're sure you know which one is yours. You've got a solid set of elements before you start into normal operations. Okay, once you figure that out, then what you want to always do is use that object number in your tracking software. You plug the name in so you know which one is yours. You can see by the name, but don't do the updates by the name. Because guess what? I've seen names move around. I claim this object set. They put my name on it. Somebody else claims that same object set. Instead of saying, wait a minute, somebody else already did that, they just changed the name. Now, if my tracking software is doing my internal updates based on name, it's updating the wrong object. Yes, sir.
The CubeSats that were launched October 28th, have they all been identified by now?
Yes. Great lead in, because that's where they were at 20 days after launch. Okay, that's those objects. And see now they're spread out. It's about 1.5 minutes to 2 minutes between horizon crossings after 20 days. And now, 9 weeks later, they've all been identified. And they're correct. At least I haven't heard anybody bitching that their name is on somebody else's. Okay. Yeah, they all are correct because all those people are using them and they're working fine. Okay, so that's what it looks like when they replace object A, B, C, D with the actual satellite name. And that's what they would look like today. If you watched them, they're 6 to 8 minutes apart in their horizon crossing times. That was as of about 3 or 4 days ago. Okay. Wow, we made 55 minutes. Questions about any of that good stuff? These first couple of 3 weeks of operation are probably the most exciting time when you build a satellite and you launch it, and holy cow, you hear it for the first time from space, you start turning things on, you see things working, and hopefully you don't see things not working. That's pretty cool. Particularly if you have a camera and you get to be the one that pushes the button that takes that first picture as you fly over your ground station. I had the opportunity with the AO-40 satellite.
Hey, Jim, this is Nate at BU.
Yes, go ahead.
Yes, go ahead. Hey, you mentioned a simulator, a power supply that would simulate the orbit with the sun on the solar panels, and I was wondering if that was an established thing, or give me some idea what that actually looks like.
Yeah, you can buy those. The question was, where do you get a solar simulator power supply that simulates a solar panel? You can buy them. You can pay a lot of money for them. HP makes some very expensive ones. But you can do the same thing simply by using a voltage and current limited power supply. When sun hits a solar panel, if there's hardly any illumination at all, the voltage will go to the max the solar panel is capable of putting out in terms of voltage. It's the current that varies as the amount of illumination and the angle of illumination. So you can set a current and voltage limited power supply for that voltage and then vary the current limit on that power supply to simulate varying amounts of illumination. If you're testing in the lab, set the voltage for the nominal operating voltage and set the current from the solar simulator power supply to enough current to make up for whatever load you're drawing while you're doing the testing. That way your power system, your EPS, is taking care of assuring you don't overcharge the battery, and yet you're able to supply enough current back in from the solar panel simulator So even when you turn things on and off, you're able to keep the batteries from dropping around the knee in the curve. Did that answer your question?
Yeah, thank you.
You're welcome. Yes, sir.
Yeah, you can also add a series power resistor to give you the droop before the knee, and then after that, the current limit should take over.
Sure.
A little bit more precise.
Yep. Other questions? Okay. Thanks very much. We'll call it good and replay.
Okay.
Thanks, Brian.
Yeah.
Thank you all.
All right. Thank you, Nate. If you want a copy of this, just shoot me an email. I'll send you a copy of this along with Dave's.